Hello everyone and welcome back to my channel. I am Sahil Sawant and I am currently pursuing my M.Tech in Computer Engineering at VJTI Mumbai with a background in Electronics and Telecommunication Engineering from VIT Pune, and also have some research experience in RF systems and radio astronomy as well. In the first episode, we understood that a signal is a variation that is carrying some information. In the second episode, we explored time and frequency domains. In the next episode, that is the third, we saw how incorrect sampling creates aliasing. In the fourth episode, we discussed spectral leakage, how finite observations are distorting frequency analysis. Today, we talk about something more fundamental, something that exists in every real system, and that is the noise. Textbooks define noise as any unwanted disturbances that are corrupting the signals. But let's understand these things physically. Noise is not just an accident, it is a natural phenomenon, and it comes from thermal motion of electrons or imperfect components, or let's say atmospheric disturbances, or cosmic background radiations in radio astronomy, or quantization in ADCs. Even if your system is perfect, nature itself introduces noise, and noise is the cost of reality. Imagine you are trying to hear someone whisper in a crowded room. The whisper is your signal. The crowd chatter is the noise that is being introduced in the signal. Now imagine trying to detect weak radio signal from the sun. The sun emits weak bursts, but your receiver also picks up thermal noise from the electronics, man-made interferences if there are any, and cosmic background radiations as well. Separating this signal from the noise becomes a real world challenge. Signal processing is often known as noise management as well. Now let's classify noise in simple terms. First, let us discuss something about thermal noise. The thermal noise is also termed as Johnson-Nyquist noise. It is caused by random motion of electrons. It exists in every resistor and it cannot be eliminated. It can only be reduced in a form. Next noise is a short noise. This short noise occurs due to discrete nature of charge carriers. It is important in semiconductors and photodetectors. Now let us look at environmental noise. Now, environmental noise is in power line interferences or RF interferences or EMIs as well, electromagnetic interferences. Now, let us look at the quantization noise. It occurs during analog to digital conversion because digital systems approximate the continuous values. Thus, we can understand that noise is everywhere, from physics to digital systems. In many engineering systems, noise appears as a Gaussian. Why? Because of central limit theorem. When many small independent disturbances combine, their sum leads to form a Gaussian distribution. That's why we model this noise as additive white Gaussian noise, also known as AWGN. White means equal power at all frequencies. Additive means it adds itself into the signal. And Gaussian means its amplitude distribution follows a bell curve. This model simplifies our analysis. Now we introduce one of the most important metrics, that is the signal to noise ratio, also known as SNR, which is defined as signal power divided by the noise power, usually expressed in decibels. SNR in decibels is known as 10 log 10 signal power divided by the noise power. Higher the SNR means cleaner the signal, and lower the SNR means buried signal, that is a little bit of noise interferences or more. If SNR is too low, your system becomes unreliable. In communication systems, low SNR means bit errors. In biomedical systems, low SNR means misdiagnostics. In astronomical systems, low SNR means false detections. Imagine plotting a clean sine wave. Now start adding the noise gradually. At first, the signal is going to be clear. Then signal becomes much more distorted. Eventually, signal becomes indistinguishable. That threshold is known as SNR dependent. So the engineers must design the systems to operate above acceptable SNR levels. Let me connect this to radio astronomy. When observing weak cosmic signals, the received power is extremely small, sometimes comparable to system noise as well. So how do we detect these real signals? So we integrate it over the period of time, average the multiples of samples, use narrowband filtering, and then apply statistical detection methods. Sometimes we observe for hours to improve our SNR, and that's how serious noise can be. Short answer, no, we cannot eliminate the thermal noise. We can just reduce its bandwidth, improve our amplifier design. We can use cooling systems or cryogenic receivers in our astronomy, or increase the signal power, or use the filtering, or apply an averaging techniques. Engineering is not about removing the noise. It is about designing around it. If the noise is random and signal is consistent, averaging multiple measurements can help reduce the noise, because random components cancel out over the period of time. But this increases our processing time as well. Again, there is a concept of trade-off in speed and accuracy. If you remember one thing today, noise is not a flaw. It is a fundamental part of physical systems. Signal processing is not just transforming the signals. It is about protecting the information from the noise as well. In the upcoming episode, we will move on to something more powerful. That is the filters. How do engineers effectively remove the unwanted frequencies? And how do we design systems that allow signals to pass but block the noise? And that's where signal processing becomes an engineering design. Welcome back again to Signals and Stars.